So section 2 of the graph theory section, my favorite unit of this class. So remind me before we get going, we talked about some basic terminology last time. What is a path? Anybody remember what a path is?
I keep mentioning that the whole not that taking walks for some reason, but the two vertices connected together.
Pretty more or less.
Basically goes back to the same.
That's a circuit. A circuit is a specific type of path that starts and stops at the same vertex. Great. And a path is just going along the edges. It's the vertices and the edges. So yes, going from one to another, but then you don't have to stop at just the one. You can keep going. That's what a path is. So what I told you last time is then in the next 2 sections, we're going to talk about specific types of paths and circuits that have good usefulness. So the first one are the paths and circuits created by the mathematician we talked about briefly last time, who invented graph theory to solve the Königsberg bridge problem, which we're going to solve today. So we're going to look at Euler paths and Euler circuits. So an Euler path has this characteristic. So an Euler path is a path that passes through each edge of a graph exactly once. An Euler path goes across every edge exactly once. You do not repeat any edges. You do not skip any edges. Okay, every edge gets passed over exactly once. And if a graph has an Euler path, it's called traversable. You can traverse the graph. So Euler paths, we're going over each edge exactly once. If I can do it, it's traversable. So in exercise 1, I have given you a graph that does have an Euler path, has several. So I would like you to take a moment. Remember, a path does not have to start and stop at the same place. I'm going to give you 90 seconds. See if you can figure out a path around that graph that crosses each edge once. Just trial and error. There's nothing's going to happen to you if you get it wrong. Did anybody find one? What is it? Tell me where you started. Okay. Okay, well, let's see. Okay, let's verify that. So said that we went from A to C, so we've crossed that edge. I'm just going to put a little mark on it. Then he went from C to E, so I'm going to put a little mark there. And then from E to B, so we crossed up through the middle. And then from B over to C, great. And then from C down to D. And then from D up to B. And then from B over to A. And that seems like we crossed every edge exactly once except for one. Which one did we skip? Okay, we did not go D to E. Okay, so that's a good attempt. I appreciate it, but that's not quite right. That's okay. We'll try again. What do you got?
D, E, C, D, E, C.
I'm going to ask you to repeat it because I'm changing colors so we can keep track. So you said you started at D and then what?
E.
Okay, E, C. Uh-huh. All right, let's see if that works. Okay, so we started at D. So we went from D to E, so we got that bottom one in. And then E to C, so we've gone up the side. C over to B, so we've gone through the middle. B down to D. Then D up to C, so we've gone through the middle again. Then C up to A, and then A down to B, and B over to E, and yes, looks like we got it on the second try. Perfect. So I'm going to give you a little hint, and I'll tell you how I know this in a minute. That's where we're driving this bus. Is in order to find an Euler path here, you needed to start at either D or E. If you started at B or C or A, you're going to end up leaving an edge out. Okay. How do I know that? Don't worry. You were just doing trial and error. Okay. That's all. So that is an example of an Euler path. We crossed every edge of that graph one time. The other one is called an Euler circuit. And we already mentioned a circuit is just a path, right? It is movement across my graph. It's going along the edges. A circuit is a path that starts and stops at the same place. So an Euler circuit, again, is a circuit. So it's a specific type of circuit. I'm going to start and stop at the same place that passes through each edge of the graph exactly once. And if you've forgotten what a circuit is, you might parenthetically make a little note to yourself above the word circuit. A circuit starts and stops at the same vertex. So exercise 2, I've given you a new graph. This is probably going to be a little easier, but find an Euler circuit. Start at a vertex and end at a vertex, and make sure you go through every edge one time only. Pardon me. All right, anybody find one? All right, give it to me. What do you got?
Okay. A, B, C, D, E, 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 F, E, C, A.
All right, I think I got all the letters. We'll see how I did transcribing. So we started at A down to B, got that edge, B over to C, got that edge, C goes to D, so got that edge, D goes up to B, got that edge, B goes down to E, yes, E goes over to D, yes, D goes to F, sure, F goes to E, yep, E goes up to C, and then up to A. Yes, you did it, you got them all, fantastic. Somebody else got one for me? Did you start somewhere different? Okay, I think so too. Let's see. So she started at E and then went to C. So got this one right here and then over to B. So got that one and then up to A. Fantastic. And then over to C. So there we go. And then down to D. So we got that edge and then up to B. Fantastic. We're doing really good. Back down to E. So we got that edge, then over to D and then F and then E and finished where we started. Excellent job. So here's what I know that you don't yet, because you're just learning this in trial and error. As long as there's not a bridge, which there's no bridge in this one, as long as there's not a bridge, when a circuit, an Euler circuit exists, you can start at any vertex and it'll work out. When there's a bridge, you got to be more careful. Okay, and we'll talk about that later. Okay, now how do I know that? Well, let's turn the page. This is the theorem Euler devised. This is how he determined whether or not he could solve the Königsberg bridge problem, which we're going to see in a minute. So here's what Euler's theorem says, is if you have a connected graph, remember we talked last time, a connected graph means that from any vertex, I can find a path to get to any other vertex, okay? For a connected graph, these statements are true. Statement 1, a graph with no odd vertices, meaning all the vertices are even. So a graph with all even vertices has at least one Euler path, which is also an Euler circuit. So here's how to summarize this, okay? If you have no odd vertices, you'll have an Euler circuit, guaranteed. I got this chart out of the book, and sometimes they use more words than they need to get to the landing spot. An Euler circuit can be started at any vertex, and it will end at the same vertex. They should have parenthetically put, unless there's a bridge. You got to be careful when there's a bridge. The second thing is a graph with exactly two odd vertices. Okay, so that's the key. Exactly two odd vertices. Has at least one Euler path and no Euler circuits. Each Euler path must begin at one of the odd vertices, and it will end at the other one. That's how I knew on that first example that you had to start at one of the lower ones. And we're going to go back and look at those two examples. And that's how I knew where you need to start and where you were going to end. And then if you have more than two odd vertices, there's neither. There's no Euler path, there's no Euler circuit. So just real quick, you don't have to do this if you don't want to, because you're going to get plenty of practice in a minute. So exercise 1, remember the way we judge the degree of a vertex is we count the edges that go to it. So this vertex A has a degree of 2, B has a degree of 1, 2, 3, 4, C has 1, 2, 3, 4, and D and E both have 3. So that's the situation where there's exactly two odd vertices. So that's how, because I've done this before, that's how I knew there was going to be an Euler path. And that's how I knew you needed to start at either vertex D or vertex E to find it. Okay, because those are the odd ones. And that was why you were able to find one starting at D. And then the Euler, the next one, vertex A is degree 2, B has 4, C has 4, D has 4, E has 4, and then F has 2. So since we don't have any odds, everyone was even. Again, that's how I knew beforehand that we were going to have an Euler circuit, and you could start anywhere and find one. So here's what I would like you to do. Exercise 3. I've given you 3 graphs right there. What I want you to do for each of them is determine, does a Euler circuit exist, or does just an Euler path exist, or does neither exist? And if you have time, find an example. Is everyone done with the first one? Let's look at the first one, see how you're doing. And then if you have a question, then I'll give you a little more time to look at the second and the third one. So on the first one, what's the degree of vertex A? 2. There's 2 edges going into vertex A. What's the degree of vertex B? 1, 2, 3, 4. That's exactly right. How about vertex C?
4.
Vertex D?
2.
E?
4.
And F.
2.
Okay. So which situation is this?
30.
This is the first situation. There are no odd vertices. So that means an Euler circuit exists here. And there's probably as many different answers to the next part as there are people in this room. You can start anywhere, and it's actually on one like this, it's kind of hard not to find an Euler circuit. Anybody got one you want to give to me? Go ahead, go for it. Okay, let's just confirm. I think I was following along and I think you got it, but I just want to make sure. So D goes up to B goes up to A goes over to C goes back over to B. Good move there. And then B goes down to E goes back up to C goes down to F, and then over to E, over to D. Yes, you covered them all. So again, there's lots and lots of answers for that problem. Okay, I'm going to give you another minute or so. Do the same thing for the second and the third problem. Determine which of the situations above applies. And if there is a Euler path or an Euler circuit, please find one. Okay, so the second one, vertex A has a degree 2, B has a degree 2, C has 1, 2, 3, D has 1, 2, 3, E has 2, and F has 2. Everybody getting the degrees? Are we doing okay with that? Okay, which situation is this one? It's the second one. We have exactly 2 odd vertices. It's those ones in the middle, C and D. So this is the Euler path. And to find one, you got to start at either C or D. You got one? Give it to me. All right, I think that's perfect, but let's just double check. C goes up to A goes over to B goes down to D goes over to C goes down to E, then we go over to F, and then up to D. Yes, we covered every one. We started at one of the odds. We ended at the other one of the odd. Okay, last example. Let's go through. Vertex A has a degree of 3. Vertex B has 3. Vertex C has 4. D has 3. And E has 3. Which situation is this one? We have more than 2 odd vertices, so none exists. Or neither exists. I don't know what's grammatically correct there. That's not my forte. Is this starting to sink in? We doing okay?
Yeah.
Okay, another opportunity to do it. Okay, basically that's everything for this section. We're just going to practice discerning the difference. So exercise 4, I've just given you 2 more graphs. determine if an Euler path or an Euler circuit exists, and then if either exists, give an example. Right, so for exercise 4, let's just go around the horn here. So A has a degree of 3, C has 3, E is 2, D has 4, B has 2. So again, this is the second situation. We've got exactly 2 odd vertices. Vertex A and vertex C are both odd. And so this has an Euler path. And to find it, you're going to start at one of those odd vertices. Anybody find one? Go ahead, bring it on.
A, B, C.
Hang on, go slow. A, D, C.
A, B, E, E, C.
All right, let's see. So we went from A down to D. That covers that edge right there. D up to C covers that edge. C back to A. Good. And then A over to B. And then over to D, over to E, and then back to C. Fantastic, you found one. Again, there's other options there, but you're going to start at one of those odd vertices and move around. The next one, what we've got is A has 2, B has 4, C has 2, 4, 2, and 4. So this is, again, one that has an Euler circuit. And you can pretty much start anywhere and you're going to find one. Let me see if I can do this and prove my worth as an instructor today. So I'm going to start as B, and I'm going to go down to D, and then I'm going to go up to F, and then I'm going to go back to B, and then I'm going to go around the outside now. I'm going to go to C, and then to D, and then to E, and then over to F again, and then to A, and then finally to B where I started, and there's my Euler circuit. Any questions so far? Doing all right? All right, we'll flip the page. So here we are. This is where we started our chapter. Okay, so example 1. This is the Königsberg Bridge problem. Okay, we drew the graph of this last time. I'm just going to redraw it real quick. It's in your notes from the previous thing. And so we're going to answer the question that the townspeople had in the 1700s. Is it possible to go over every bridge one time? They didn't have TV, so they needed something to entertain themselves. So again, I'm going to make the land at the top vertex A. I'm going to make the island on the left vertex B, the island on the right vertex C, and the land at the bottom is going to be vertex D. And then from the land to the island on the left, we have 2 bridges. Again, we did this last time. That's why I'm going a little faster through this one. From the land, we have 1 bridge going over to the right. From the island on the right, we've got 2 bridges going to D. And then we've got a bridge that connects the 2 islands. And then last but not least, the last bridge that goes over to the land. So there is the graph that hopefully looks sort of familiar because we drew it in class last time. So now if you're Leonhard Euler and you invented a whole branch of mathematics to solve this problem, which is pretty amazing to me. So here we go. A has 3, C has 3, D has 1, 2, 3, and B has 1, 2, 3, 4, 5. And so the question, Can a person plan a walk and cross each bridge exactly one time? And what's the answer to that question? No. You'd have to repeat. So thank you, Dr. Euler. So exercise 5, what I did is I found a picture that let's pretend the Königsberg people built another bridge because they were really into this, wanting to cross them all once. And so now they want to know, can they do it now? So I don't think this is the same as the picture we drew a graph of last time. So draw your graph and determine, can we cross each bridge once? All right, so here's the graph I drew. So remember, each bridge is an edge. So we've got 2 bridges from the land at the top over to the island on the left. We've got 1 bridge from the land on the top to the island on the right. We've got a bridge connecting the 2 islands. We've got 2 bridges from the island on the left over to the land on the bottom. And then here's the change from the previous drawing. We've got 2 bridges from the island on the right over to the land on the bottom. So now when I go ahead and I do my degrees, vertex A is degree 3, vertex C is degree 4, D is degree 4, and B is 1, 2, 3, 4, 5. So now, yes, we can. Okay, we see that we have exactly 2 odd vertices, so an Euler path exists. We can cross all the bridges exactly once. So if you were planning out your Saturday night and you wanted to be wild in the 1700s, then what you would do is you'd start at one of either the land at the top, or you'd start at the island. I'm going to start at the island. And then we're just going to go ahead and we're going to navigate and cross all the bridges once. So we go from B down to D. Let's try that. And then from D, let's go back to B. Sure. And then from there, we're going to go up to A. And then from A, I'm going to go back to B because I'm really digging that island right there. Then I'm going to cross over to C. And then from C, I'm going to go down to D. And then I'm going to go back to C. And then finally, I'm going to end up at A. And there's my Euler path. Questions, comments, concerns? We doing okay? Because again, we're just going to keep practicing this. All right, well, I'm trusting that you're telling me the truth. No reason to not to. Example 2, again, this is another situation. We drew a graph for this in class when we were together and we were practicing graphs. So I'm just going to real quick reproduce that graph that we had. So remember what we were doing is the ability to go across a border represents an edge. So each state, we're going to make a vertex. So California and Nevada and Utah and Colorado, and then I've got Arizona and then New Mexico, which I'll let be NM. So this part's not new. That's why I'm going through it a little quicker. So from California, California shares a border with Nevada and with Arizona. Nevada shares a border with Utah and then Arizona and also California, which we've already got. Utah shares a border with Arizona and Nevada, which we already got that one, in Colorado. Colorado shares a border with Utah and New Mexico. And finally, New Mexico has Colorado and Arizona. So then the question is, can I go through this graph and cross each edge one time? Okay, so let's see. Let's do what we've just done for the other ones. California has degree 2. Nevada has degree 3. Utah has 3. Arizona has degree 4. New Mexico has degree 2. And Colorado has degree 2. So once again, this is the situation where I've got exactly 2 odd vertices. So I can cross each edge. I can go across each border of the state exactly one time. Where do I have to start if I want to do this? Not Nevada or Utah. Yeah, one of the odd ones. Exactly. However you answered that question. Doesn't matter. Let's start at Utah. Where should we go from Utah? Sure, why not? Colorado sounds great to me. And then from Colorado, we're kind of predestined to do this next. We have to go into New Mexico. So I'm going to put an NM there. And from New Mexico, we have to go to Arizona. There's no real choice there. Okay. From Arizona, where should we go? Sure, let's go to California. Sounds great to me. And then California, I have to go to Nevada. And then from Nevada, I have a choice. It doesn't matter which one I go. I'm gonna end up in the same place. So let's just go down to Arizona and then back up to Utah. And then finally, we're gonna end in Nevada. And there we go. We started at one odd vertex. We ended at the other odd vertex. All right, if you're feeling good, that's great. If you're not, I hope you would ask me a question because we're just going to continue doing the same thing. So exercise 6, I don't remember if we used this as one of our examples last time or not, but go ahead and draw your graph and determine if we can find an Euler path or an Euler circle. All right, so according to this map, from Texas, I could just go into Louisiana and that's it. From Louisiana, I can go to Mississippi and that's it. Mississippi goes to Alabama, so not a whole lot interesting so far. Alabama, you can go into Georgia and you can go into Florida. Georgia goes into Florida and Alabama, which we've already got, and South Carolina. And I think that's everything. So now let's look at the degrees. So Texas has a degree of 1. Louisiana has 2. Mississippi has 2. Alabama has 2. Florida has 2. Georgia has 3. And South Carolina has 1. So there, no, I'm sorry, I miscounted on one of those. Alabama, 1, 2, 3. Sorry about that. So this is the situation where I've got more than 2 odd vertices. So there is no path. I cannot go through each state border exactly one time. Same thing for exercise 7. Draw the graph. Determine if you can cross each exactly one time. So on this one, from Turkey, I can go several places. I can go down to Syria. I can go into Iraq, and then I can go over here and go into Iran. So lots of choices. Syria goes into Turkey, which we've already got. It goes into Iraq, and then it goes down to Jordan. Jordan, you can go into Syria. You can also go into Iraq. So we got to put that edge. Iraq, we've already got the edges into Turkey, into Syria and Jordan, and you can also go into Iran. Iran, we've got Turkey, we've got Iraq, and then we've got Afghanistan and Pakistan. And then last but not least, we've got to join Afghanistan and Pakistan together with an edge. So then the question is, can I cross each of those borders one time? So Turkey has degree 3, Syria 1, 2, 3. Jordan has degree 2, Iraq 1, 2, 3, 4, Iran 1, 2, 3, 4, Afghanistan has 2, Pakistan has 2. So the answer to the question is yes, we can find an Euler path on this one. So I don't know where you started, but you only have 2 choices. And then once you pick one of the 2, finding the path I don't think is super bad. So you're either going to start at Turkey or you're going to start at Syria. Those are your only options for where to start on this journey you're going to take. So I'm going to start up at the top at Turkey. I'm just picking that for no particular reason. And so then we're going to go from Turkey down to Iran, Iran up to Afghanistan, Afghanistan down to Pakistan, Pakistan back to Iran, Iran over to Iraq, and then from Iraq, I'm going to go over to Jordan, and then up to Syria, then back down to Iraq, and then up to Turkey again, And then last but not least, we get into Syria, and that ends my road trip. All right, so this is my last example for the day, and then I just got some problems for you to finish up. This is another graph. We did this. We made the graph that represented this gym when we were together last time. So again, I'm going to redraw that. I've got the outside up here, and then I've got Ray's room, and then I've got locker room A, and then Sierra's room, and then the health and weight room, and then Keegan's room, and then locker room B, and finally Chet's room. So we did this with the doorways. Again, you can look in your notes and just use it there if you have that page with you. I didn't bring that page with me. So from locker room A, I can go outside, I can go into Sierra's, I can go into Ray's. From Ray's, I can go into locker room A, I can go into the health and weight room. From the health and weight room, I can go into Ray's, I can go into Sierra's, and I can also go outside. And if you remember, I told you we could draw these edges through the other ones, but just to avoid any confusion that might engender, I'm going to go ahead and draw these two doorways around like that. And then Keegan's goes into the health room and also into locker room B. And locker room B goes into Chet's, and Chet's goes into the health room. So I think we covered all of our edges. Again, went through that pretty quick because we drew that the last time when we were together. So the same question is, if you were responsible for locking all the doors and you wanted to just save as much energy as possible, could you go in a route that lets you pass through each door one time? Meaning, can I cross every edge of this one time? Well, let's see. Outside has a degree 3. Locker room A has degree 3. Sierra's has a degree 2. Ray's has degree 2. The health center has 1, 2, 3, 4, 5, 6. Keegan's has 2. Locker room B has 2. And C has 2. So yes, it is possible. You either have to start outside or you have to start at locker room A, and you can go through and traverse this and just cross one edge every edge exactly once. Somehow I'm going to say that right. So here we go. Doesn't matter where we start. I'm going to start outside just for kicks. And so from outside, I'm going to go into the health room. And then from the health room, I'm going to go up to Ray's. Ray's, go over to A. From A, I'm going to go over to Sierra's. Back into the health room. Down into Keegan's. And you probably have a different path because once you pick one of those two to start with, there's probably dozens of ways you can go around this and go through every one of these edges. So if you have one that looks a little different than mine, that is the most likely scenario. And then if you start at O, you're going to end at A. If you started at A, you're going to end at O. There's no choice. Euler has said it has to be so. All right, so you just have a few more problems. So we're probably going to get out of here a couple minutes early. If you got any questions, please bring them up. We got plenty of time. There's absolutely no reason to rush. So do the same thing for exercise 8. That's a little bit of a simpler floor plan, and determine if we could go ahead and find a path that goes through every door once for that. All right, so each doorway represents an edge. So if you're in room A, you can go to room B or you can go to room D. If you're in room B, you could go back to A, or you could also go to C, and that's all you can do. B is landlocked in there. C, you can go out to B, you can go down to E. From E, you can go back to C, or you can go outside. And then the only other one is D, you can go back to A or you can go outside. So this is not a very creative looking little graph, so pretty casual example. All of the vertexes or vertices, I knew I would do that at some point, all the vertices have a degree 2. And so yes, and you can find a circuit, you can start at any vertex and you're just going around this loop. So whatever you picked. So if I started at A, I'd go A, B, C, E, O, D, and back to A. So yes, it's possible to go through all the doorways once if you wanted to. So any questions before we hit the last page? All right, so this is your exercise. You drew this graph in class last time. This was one of your examples. So if you don't have that with you, just go ahead and reproduce that graph. Remember, every intersection is a vertex. And we had the discussion in class about these corners. And since those are the intersection of two roads, we made those vertices. Almost did it again. I really love saying vertexes for some reason. And then go ahead and determine if I'm a security person, can I drive along each road one time exactly? Gas costs a lot now. I don't want to waste any. All right, so here's my graph. I labeled the vertices. It doesn't matter what you labeled them. You probably did something different or a different order than I did. So if it comes up that we have to go around this. So A has a degree of 3, B has a degree of 3, C is 2, E is 2, D is 4, F is 2, G is 2. So yes, it's possible for the security person to go ahead and go around this one time. Going to start at either of these top vertexes. I'm just going to go with it. Start at either one of these two odd vertices, and then you're going to end at the other. So whatever. Did anyone figure out a path around?
Yes.
Go ahead. Okay. All right, I trust you, but let's just confirm A to D. I'm assuming we're on that loop, but it doesn't matter. And then back to A. So there's that. And then over to B, then over to C, and then down to G. Gotta kind of have to go this way, and then up to D, and then over to E, and then up to B. Fantastic. That looks beautiful. Well done. All right, so here's how we're going to finish. We've got 4 more graphs. So what I want you to do for these last 4, for all of them, I want you to determine if a path or Euler path or an Euler circuit exists, and then just pick one and find it. Okay, so pick one of the ones that does. I haven't done any of these problems, and go ahead and find it, and then we'll compare notes, and then we will be done for the day. All right, I'm going to start with the top left graph. So here goes. I asked you to determine Euler path or Euler circuit or neither for all 4 of these, and then to pick your favorite and find either the path or circuit, whatever it has. So this first one, vertex A is a degree 3, vertex B has a degree 3, C has degree 2, D has degree 4, and E has degree 2. So this one has an Euler path because it has exactly 2 odd vertices. Did anyone pick this one to find to traverse? Go ahead. What did you come up with?
A, B, D. A, B, D.
Hang on, you said A, B what?
A, B, D.
A, B, D. Okay, great.
E, B. A, B, C. A, B, D.
Okay, so we can't go to A, B to C. There's no edge from B to C. That's what got me before. So we'll have to try something different. So let's do this. Let's go from your A to B. That sounds great. But then what we have to do from there is let's go to E. Go down here. Then we'll go over to D. And then we will go back. We'll go over to C. And then we'll go up to A. And then we'll go down to D, and then we'll go back up to B. So we started at the first odd vertex A and ended at the second odd vertex B. All right, so that is that first example. Next one, vertex A is degree 2, B is degree 2, E has degree 2, F has 4, B has 2, or I guess that's an H. I'm not wearing my glasses. H has 2, G has 2, D has 2, and C has 4. So this has an Euler circuit. We have all even vertices. There's no odd ones at all. And so basically in this situation, you could start anywhere. Anybody find one? Did you do this one? Go ahead, give it to me. A to B, great. Okay, it's looking good. Sure thing. Okay, so we're going to go from F up to C, great. Okay, good choice. Okay, we're going to go over to H. I'm going to move down to the next line to G. Yep. Back to A. Perfect. Well done. Excellent job. Okay, the second to last problem down here. So A has degree 3, B has 4, C also has 4, D has 2, E has 4, F has 4, lots of 4s, G has 3, H has 4. So this, like the first one, we've got a path that we can find, and we've got to start at either A or G. Did anyone do this one? Go for it. What do you got? Okay. H to what did you say? Okay, thank you. All right, so let's see how that worked. It sounds impressive. So A to G we went, and then G up over to H, and then H over to B, and then B back to A. So far so good. Then to C, and then up to B, and then down to E. So you're doing good. And then H, yes, and then to F, yes, and then to from there to D, sounds great, and then to C, then to E, to F, and then to G. Excellent job. We traversed that. Well done. All right, the last one. This lovely triangle that we've got here. We've all right, so we are back. So here goes. So this last one, A has degree 2, then degree 4, and then degree 4 again, and degree 2, 4. I think there's a lot of 4s here, and a 2 and a 4. E has 1, 2, 3, 4. Let me see, 1, 2, 3, 4, 5, 6. C has degree 4. So this last one has a circuit. All right, and so since we have a circuit, anybody do this one? You were ambitious. You did more than one. Sure, bring it on. What do you got?
A to B, C, C to E, E to B, E to H, E to G, G to H, H to I, to F, E.
All right, so here we go. We're just about done. So A to B, then over to C, and then to E, which I covered up, so I almost lost it, and then back up to B. That sounds great. Down to D, and then to back over to E again, then to H, and then to D, then down to G, then to H, and then over to I. Sounds great. You're doing a wonderful job. Up to F, back to E, back to I, over to J, up to F, to C, to A. You did it. Great job. You traversed the graph.